Yeah, first off, just want to thank everyone for attending this webinar. I don't claim this to be a groundbreaking or revolutionary presentation, nor do I consider myself an expert in this area. However, I do believe I have a pretty decent grasp on some of these concepts and hopefully can distill them into easily digestible bits of information. Like much of the material that we get in this area is typically exposed during either undergraduate physics or biomechanics courses, but often I feel like it gets lost by the time that we reach physical therapy school. And I think there's this assumption that we retain this foundational understanding, yet biomechanics and PT education tends to focus heavily on arthrokinematics and osteokinematics, with little emphasis on the physical principles that truly govern movement. So this webinar aims to hopefully kind of fill that gap. So here's going to be a list of some of the objectives for today. It's going to be here more for your reference. I don't want to bore you with just leading or listing off this entire list here. So we'll get right into things here. Um, so physics underlies everything we do in sports rehab, from managing swelling through fluid dynamics to restoring strength via torque and force production, to progressing plyometrics based on load, velocity, and ground contact times. All traces back to the first principles of movement, which we kind of define as physics. And understanding these principles isn't just academic, it's the foundation for making more informed and effective clinical decisions. So we're going to take a month by month approach to ACL rehab using key physical and biomechanical principles to kind of help guide progression. As a disclaimer here, there's going to be significant overlap between phases. Goals and qualities often kind of bleed into one another, and milestones like running or jumping may happen earlier in real world rehab. This is meant to just to highlight kind of the physics within the sports rehab realm. So for month one here, one of the primary goals during the fun or first month of rehab is to get the knee as quiet as possible, trying to minimize pain and swelling. So Bernoulli's principle is going to state that as the speed of a fluid like synovial fluid increases, the pressure it exerts decreases and vice versa. So in early rehab, gentle joint motion can help increase synovial fluid flow, increase fluid velocity, and reduce intra-articular pressure, which may in turn improve quadriceps activation. Both joint motion and muscle contractions play a role in clearing excess fluid from the joint. When the knee remains static, intra-articular pressure is often at its highest, so the aim is to encourage frequent bouts of low intensity movement, enough to stimulate fluid dynamics, but not so intense that it worsens swelling. And we can kind of see here that we have these two circles on the right. So we have pressure one here on the left and pressure two on the right. If this stays constant and that stays constant, then all we're doing is essentially just adjusting the V on each side. If this goes down or is zero, pretty much, this means this has to be high, and vice versa. If we increase this side here, this is going to have to decrease there. All right, so we're going to say the primary focus of month two is going to be quadriceps activation. We can examine this through the lens of the length-tension relationship, which describes how a muscle's ability to produce force depends on its length and sarcomere overlap. So when a muscle is either overly shortened or overly lengthened, sarcomere overlap is suboptimal, limiting active force production. In contrast, mid-range muscle lengths tend to maximize overlap and force output. So early in rehab, the goal is to restore basic quad engagement, but the true emphasis is going to lie in regaining active control of terminal knee extension, particularly into hyperextension, as this is going to have the greatest carryover to normalized gait mechanics. Unfortunately, the length tension relationship is least favorable at end range extension. Sarcomere overlap is poor. Neural drive is also diminished in this position, and typically intra-articular pressure is also high as well. So in effect, we kind of get this triple whammy effect, which makes early activation especially challenging. So a multimodal strategy targeting the quadriceps across its full range can help overcome this barrier. So emphasizing volumes of isometric work at around 60 degrees of knee flexion, where force production is greater, may offer more effective strength adaptations than simply trying to hammer away at terminal knee extension exercises like heel pops. So still getting control into hyperextension remains a necessary milestone in this process. All right, so once we've achieved better quadriceps activation, we can begin to more effectively load the muscle to build strength and improve hypertrophy. So the key biomechanical principle here is going to be torque, which is going to be calculated as
Wait,
the,
switch your slide.
oh shoot, sorry, my bad. Thank you. Um, So yeah, the key biomechanical principle here for month three is going to be torque, which is going to be calculated as the distance from the fulcrum to the point of force application or center of mass, multiplied by the sine of the angle at which the force is being applied. And remember, this is the force being applied to the lever, not necessarily joint angle. So in rehab, this often plays out through a combination of squat-like patterns and knee extension exercises. So leg extensions are going to be relatively straightforward. Isolate the quadriceps, which is that sole contributor to knee extension, which allows for direct loading. However, in compound lifts, multiple joints and levers are going to be involved simultaneously. And this is where understanding torque becomes critical, how different movement patterns shift load across joints, and how compensations can reduce quadriceps demand by altering leverage or movement strategy. So the image on the left here, we can see the individual has a more pronounced forward trunk lean with the hips pushed back. If we estimate the center of mass to be where that barbell is and draw a vertical line straight down, there's a relatively large moment arm for the hip extensors and a much smaller moment arm for the knee extensors, effectively reducing the mechanical demand on the quads. In contrast, the image on the right shows the use of external constraints to limit compensation. The primary constraint here is the post, which prevents the hips from shifting too far back and encourages a more upright trunk position. This setup increases the likelihood of directing more mechanical stress to the quads.
Behind only LeBron James. And just 2 summers ago, he showed up with Rucker Park in Holland as
Joey,
a 14-year-old.
Joey, can you mute them?
Later at 14 miles.
Yeah, I'm just trying to figure out how NBA highlights sounds like.
Perfect. Thank you. All right. So we're going to keep continuing here. So in month four, while we continue to build a quadricep strength, it's important not to neglect other joint regions, particularly the calf complex. Functionally, the calf operates as a second-class lever where the load is positioned between the fulcrum, which in this case will be the metatarsophalangeal joints, and the effort arm, which we're going to call the Achilles tendon. So the quadriceps and calf muscles often work in synergy, especially during gait and deceleration. So adequate calf strength is essential. Unfortunately, I feel like calf training is often underutilized in ACL rehab, despite evidence showing prolonged gastroc atrophy post-injury. And also, the soleus is going to act as a synergist to the hamstrings, contributing to limiting anterior tibial translation. So while standing calf raises are typically performed well, with only minor cueing needed to avoid compensation, bent knee variations, especially in standing positions, are often poorly executed. This is primarily because the load vector remains stationary while the shank moves through space, reducing true tissue loading. So many mistake this movement for effective training, when in reality, it's more of a case of sensation being confused with the actual stimulus. So in the middle image here, we observe two key issues. One's the primary load vector is positioned outside the lever arm, which is going to be that red line here being outside kind of this area there in the foot. And two, the load that's moving isn't the resistance itself. So what's actually moving is just this limb right here, the tibia, just in space, not this line here. So this limits the mechanical demand on the soleus. So to more effectively strengthen the soleus and target the appropriate tissues, we need to ensure that the load vector actually moves. So this can be achieved by introducing proper constraints to maintain alignment and reduce compensation. So with the image on the right, we use that roller to kind of control that position or constrain the position of the knee, the wall to prevent any sort of momentum based compensations. And then we have that primary load vector kind of going right through the foot ankle joint there. And this is going to help create a more meaningful mechanical stimulus. All right, so in month five, as strength continues to improve and more dynamic tasks are going to be on the horizon, such as running, jumping, and change of direction, we need to develop the quadriceps ability to produce force under high velocity conditions. A concept that often gets misapplied here is the force velocity curve, and in many cases, what people probably are actually referring to is more the load velocity curve. So force velocity is going to refer to the force a muscle fiber can produce at varying contraction speeds, while load velocity refers to the velocity of a movement pattern under different external loads. So is it force velocity or load velocity? The answer probably depends, probably likely on the context, and probably it's often both. So in isolated testing scenarios like isokinetic dynamometry, especially with the quadriceps, we'll probably see a classic force velocity relationship. As speed increases, let's say from 60 degrees per second to 180 degrees per second, the muscle's ability to generate force declines. However, in more global or gym-based movement patterns, the load velocity curve is probably more applicable. I think it's important to recognize when the force velocity model starts to break down, particularly when applied to sprinting or plyometrics. So these activities are often mislabeled as low force based on their load alone, when in reality they involve very high forces generated and absorbed in extremely short time frames. So understanding this distinction can probably help guide programming, especially when it comes to programming plyometrics. So let's take a look at the force profile of different exercises under different velocity and loading conditions. So on the x-axis, we have velocity going from rough approximation of low to high. And then on the y-axis, we have force in newtons. So as we can see here, the pogos, rebound jumps after counter movement jump, and landings from a 17-inch height produce significantly higher ground reaction forces than so-called high force exercises like the isometric mid-thigh pull or 315-pound front squat. So this kind of highlights the idea that what we often perceive as high force may be better understood through the lens of the load velocity curve. From a rehab perspective, the goal is to strategically surf the load velocity curve, recognizing that different loading zones may carry over more effectively to specific adaptations. And roughly as a general heuristic, typically heavy loads are best for developing strength, moderate loads tend to benefit power better, and lighter loads are typically more ideal for speed. So understanding where your exercise selection falls on this curve allows for more intentional and targeted programming throughout the rehab progression. All right, so we're going to keep things moving here. In month 6, we're going to focus on running, jumping, and plyometrics. While many individuals begin light jogging probably around the 4-month mark, we've just chosen to include it here to follow a logical progression from strength to power to more explosive plyometric-based movements. So for month 6, we're going to apply the impulse momentum relationship, which states that force multiplied by time equals a change in momentum, which momentum is going to be that mass times velocity. So in most athletic contexts, since mass remains constant, the equation becomes more about changing velocity. This concept is especially relevant as we begin to progress jump training and plyometrics. So if we hold impulse constant as ground reaction forces increase exponentially, as we increase ground contact times in a linear fashion, so from 0.15 seconds all the way up to 0.5, we see that force tends to decrease in a linear fashion, or if we want to look at it from the flip side, as an individual can get off the ground quicker from a same drop height, that force is going to increase exponentially. So from an exercise perspective, the 3 most easily manipulated variables are going to be mass, velocity, and time. And how we adjust those will directly affect the loading strategies we use in our plyometric progressions. All right, so we're going to go with the work energy theorem next, which is going to state that the work done on an object is equal to the change in its kinetic energy, which kinetic energy is going to be that half that mass times the velocity squared. So in the context of sport, this is going to apply directly to tasks like change of direction, where athletes must absorb and redirect momentum. And assuming an athlete's mass, entry velocity, and deceleration distance are constant, the cutting angle becomes the key variable influencing the total work required. So smaller angle cuts between like 0 to 45 degrees are going to demand less from a deceleration standpoint and therefore less work. But as the cutting angle increases from 60 to 90 up to 180, the athlete must perform more work to redirect momentum, leading to a higher mechanical demand on the body. So now let's connect this to jumping mechanics. So in horizontal jumps, the propulsion is primarily generated by the hip and the ankle, which means distance alone may not tell us much about the quadriceps performance, i.e. with our traditional hop test. However, the landing phase is a different story. Here, the knee plays a major role in force absorption, making horizontal landings a useful proxy for assessing horizontal braking capacity. And this becomes especially relevant when preparing athletes for higher angle change of direction tasks. And in contrast, vertical jumps typically involve more even contributions from the hip, knee, and ankle during both takeoff and landing. These offer a general measure of lower limb power, but may not reflect the horizontal braking demands needed in cutting and deceleration. So to better understand how the body responds to these loads, horizontal hop landings may provide insights into how much stress the knee joint and supporting tissues must absorb. And this just reinforces the need for targeted quadricep strength and lower limb loading strategies, especially during the later stages of rehab, to better prepare athletes for the mechanical demands of sharp change of direction movements and hopefully support a safe and effective return to sport. So we're going to break this down with a visual example. In the top image here, we have an athlete entering cone B at 10 miles per hour, which gives them a specific amount of kinetic energy at that moment. Since it's a 180-degree cut, the athlete must decelerate to a zero velocity before reversing direction, and that deceleration is going to require a certain amount of work to be done. Now let's contrast that with an entry speed of 15 miles an hour. If all other variables stay the same, especially the deceleration distance, then the higher entry velocity results in greater kinetic energy at cone B, and because of that, more work must be done to complete the change of direction task. In this case, distance remains constant, so it's the force that must increase to meet the higher energy demand here. All right, so as athletes start to near the end of ACL rehab, high-speed decelerations become a critical area of focus. These movements can be better understood through Newton's third law, which states that for every action, there's an equal and opposite reaction. And in practical terms, the force an athlete applies into the ground is met by an equal force return from the ground back into the body. And at this stage, horizontal braking capacity is especially important as many ACL injuries occur during high-speed decels. While earlier discussions that we highlighted or that we talked about highlighted how cutting angles influence braking demands, true high-speed decels present an even greater challenge. These forces can reach up to 6 times an athlete's body weight, absorbed through a single limb and in a very short time frame. So when that foot contacts the ground, it delivers a high force into the surface, which in turn pushes back with equal intensity, emphasizing the need to prepare the musculoskeletal system to withstand these loads. So the challenge is going to lie in designing exercises that approximate these forces. So for instance, an athlete weighing, about 195 pounds or about 870 newtons, they're going to be able to, or they're going to have to be able to withstand about 5,200 newtons of force during high speed decelerations. I would say as a profession, we tend to often overestimate the ground reaction forces generated during lower intensity drills like snap downs and tend to, overestimate, the ground reaction forces generated by lower intensity drills like snap downs, and then underestimate the true demands of higher intensity plyometrics. And I think recognizing these distinctions can be beneficial for better drills or better exercises to kind of help get towards the rigors of high speed decels. So we're going to take a look at some common exercises shown on the graph on the left. So the chart displays peak ground reaction forces during jumping. It's going to either be braking or propulsion. So you'll see land typically as referencing the land of that jump. And these are going to be landing tasks using both double leg and single leg counter movement jumps. So the values represent the force experienced by a single limb. And as we can see, none of these peak forces come to approximating the demands of high speed decelerations. Now, if we look at the graph on the right, we begin to see better approximations. So it includes altitude landings from various heights. And it took me stepping off a 30-inch box and landing on one leg to generate peak ground reaction forces around 6 times my body weight, which is going to be comparable to forces experienced during a high-speed decel. While there are going to be differences in the direction of force application, these types of tasks at least begin to impose similar stressors in terms of ground reaction force exposure, making them more relevant for late-stage return to sport prep. And if you're in a low-tech clinic, this might be an easy way to kind of progress in terms of getting the system accustomed to similar stressors of high-speed decels. And then finally here, we're going to arrive at month 9. This is a critical phase where athletes are nearing return to sport and likely undergoing formal testing. So here we're going to use Newton's second law, F equals ma. In this context, it might be helpful to also think about it as acceleration equals force divided by mass. So using force plates, we can evaluate an athlete's ability to both accelerate and decelerate, giving us key insights into explosive power and braking capacity. So beyond raw force output, the shape and smoothness of the force time curve provides a window into neuromuscular efficiency. So a smooth, well-defined curve suggests coordinated motor control, while a more jagged or inconsistent curve may reveal underlying neuromuscular deficits. These irregularities can signal that the system isn't yet firing efficiently, highlighting areas that still may require targeted intervention before the athlete is truly ready to return to sport. So let's take a look at some real force time graphs here from an athlete currently going through ACL rehab. This individual is a high school junior football player who underwent ACL reconstruction using a patellar tendon graft. So at the 12 weeks post-op here, we can see that peak force production is relatively low, and the overall shape of the blue line representing the total force output lacks smoothness. When we break the data down by limb, we see the left leg or the purple line producing a smooth, steady curve, indicating good neuromuscular control and consistent force production throughout the task. In contrast, the right leg or the orange line shows a more jagged, erratic curve, suggesting difficulty with neuromuscular control, especially during higher velocity demands that require rapid force production. Now let's fast forward 6 weeks later. Between these two time points, the athlete continued to work on strength development, rate of force development in both eccentric and concentric phases, and the progression of jump variations, both loaded and unloaded. The updated graph shows a clear improvement in the braking phase with a smoother, more coordinated force curve. And this likely reflects improvements in rate coding, rate of force, and rate of torque development, and likely inter and intramuscular coordination, all essential for restoring efficient movement and preparing for return to sport. So I think physical principles form the foundation of everything we do in sports rehab, particularly in post-operative care. And while these concepts are often introduced early in our academic training, they can sometimes fade into the background in clinical practice. As a result, articulating how changes in specific variables influence task demands can be challenging. And I think to advance our practice, in general, it's essential to develop a deeper understanding of the physical constructs that govern human movement and how they shape exercise selection and progression. I think once these foundational principles are in place, we can begin to layer in other perspective, whether it's neuromuscular control, motor learning, movement variability, other sort of different lenses, to start to build a more comprehensive and adaptable rehab strategy. And lastly, here we also have a free ACL lecture as well, titled Ecological Dynamics, addressing interlimb and interlimb compensations in ACL rehab. If you haven't already signed up for that one as well, you can. Essentially, I think it was the month 3 slide where we talked about different constraints, or that one constraint with the post. Essentially, it dives into all the different sorts of constraints that you can use for different types of exercises, goes a little bit into change of direction and plyos in terms of different constraints that we can consider using there. So I'll keep this up for a little bit if you guys want to scan that if you have not already signed up for that.